Hi everyone, my name is Juan Pablo Izquierdo, and today I'll be doing a presentation on Systems Analysis and Design, also known as by the acronyms SAD. Through Systems Analysis and Design, I'm going to go over the following concepts such as data flow diagrams, data flow diagram symbols, the rules of data flow diagrams, processes to avoid in data flow diagrams such as spontaneous generation, black holes, and gray holes. Also, the difference between a context diagram and a diagram zero. And lastly, leveling and balancing. So to start off with data flow diagrams, these type of diagrams are visual representations of data that flows through a process or system, as seen here below in the image. Systems analysts use graphical techniques to describe such information system. It uses various symbols to show how the system transforms input data into useful information. As you can see, the symbols here have different shapes and it represents different meaning among how data is processed through the diagram. These symbols represent the system's data flow direction, inputs, outputs, storage points, and to be more specific, sub-processes. A data flow diagram shows how data moves through an information system, but does not necessarily show how the program logic or processing steps work. So it's kind of a more generalized view of the project. And it basically, a set of data flow diagrams provides a logical model that shows what the system does, but not necessarily how it does it. Now moving on to the symbols and what they mean, I'll be showing specifically the gain and Sarsen symbols, which is another popular one compared to the Jordan symbols. But because the textbook uses these symbols, I'll be using these symbols as well. And both versions are good, but today I'm showing the gain and Sarsen symbols as they are used in the textbook. So to start off with the process symbol, which is the one in the middle here, it's often referred as a black box. The black box concept means that while the inputs, outputs, and general functions of the processes are understood, the internal details and logic remain hidden. So just as I explained previously. This approach helps create data flow diagrams that depict system functionality without any unnecessary clutter. So that generalized view makes it very easy to see and understand what's going on within the information system. Although detailed data flow diagrams can show internal workings, uncovering more processes, data flows, and also data stores. Now moving to data stores. A data store, which is right here, is a symbol that represents stored data that the system utilizes for future processes. For example, let's say a student goes through a semester to assign a final grade. It needs a data store to store such data. Similarly, companies store employee salary and deduction data annually from a W-2 form preparation. A data flow diagram does not detail the concepts of a data store specifically, because the specifics are outlined in the data dictionary, which is different than a data store symbol. And then in the entities, which would be the entity symbol, which are seen here, these two rectangles, an entity symbol in a data flow diagram is represented by a rectangle, of course. So it looks similar to the process symbol, but the process symbol has curves around the edges. It's often shaded to have a three-dimensional appearance with the entity's name inside. So that's what makes it differentiated from a process symbol. Entities in data flow diagrams are also referred to as terminators, as they serve as data origins or final destinations. Data flow diagrams depict only external entities that either provide data to the system, so back and forth between a process, or receive output from it, which is illustrated here. And let's say a few examples from entities could include customers submitting orders, patients supplying data to medical record systems or homeowners receiving bills. It could have many other examples. Now, system analysts may designate entities that provide data as sources and those receiving data as sinks. An entity's name typically represents a singular form of department, organization, information system, or a person. These external entities in data flow diagrams can function as sources, sinks, or both, but each entity must be linked to a process by data flow. So as I explained here just a couple seconds ago. And now for the rules of data flow diagrams with the use of the symbols that we previously just discussed. We use these 4 symbols, the processes, the data stores, and the external entities. But in order for the information system to make sense visually, the processing must have an input and output data flows that correspond in a logical manner. So process to process is acceptable. A process to an external entity, and this is back and forth too, as you can see the 2 arrows, and process to data store. Although external entity to external entity cannot be done or with a data store or between data stores, there always must be a process involved for such data to be processed into information, which is what data is. Useful data is information, data with context. So without the process, the rules of DFDs apply to it only when the process is involved. So data stores must be connected to processes that read from and write to them. That's the meaning of the 2 arrows here. And now for processes to avoid in data flow diagrams, we have a spontaneous generation, which will be here as my first example. As you can see, this is a process that has no input, and the process is called a pay stub results. So it's giving you how much of tax was deducted from the pay stub and any 401k contribution. But as you can see, there's no error going into the process. Therefore, there's no input. Therefore, is considered a spontaneous generation. Now moving on to a black hole, this would be example 2 here. And we have a calculating college attendance cost. So we have information or data coming into this process known as the tuition and housing costs to attend a total calculated of college attendance. So why is this called a black hole process? Is because it has a process that has inputs into it, but it has no outputs. So how are we going to use this information that we have to calculate attendance costs? It's not going anywhere. So it's called a black hole for that reason, because that is going nowhere. Now for a gray hole, which is this example here, we have a calculating item price process. So we have these 2, name of store coming into the process of calculating item price, and then output data of total costs. So what makes this a gray hole is that this process has at least 1 input, as you can see, and an output. But the input is insufficient to generate the output shown. So this input right here is not relevant data for the processing of calculating item price and therefore have a total cost. Since this input is not relevant to the process of calculating a total cost, it is considered a gray hole. Now moving on to the difference between context diagram and a diagram 0 is that a context diagram is the left one here and the right one here is a diagram 0. A context diagram offers a broad view of information system and usually contains 1 process symbol right here. This process symbol, also known as a black box, as I previously mentioned. A data flow diagram 0 here provides a detailed overview of the system, highlighting major internal processes, data flows, and data stores. As seen here, is a little bit more complex than the context diagram. So it zooms in on the system, showing how its components interact to form the overall structure. And diagram 0 maintains consistency with the context diagram by repeating entities in data flows. So as you can see, student, student, student record system, student record system. So the integrity stays there, but it's just more detailed. All connections flowing into and out of processes 0 in the context diagram must be preserved when expanding into the data flow diagram for it to be consistent. Now moving on to leveling and balancing. On the left, leveling, and on the right, balancing. And this can be sort of confused at times. But this is the basic example that I took inspiration from on my textbook. And these are the images that I got from my textbook that are more detailed and more easy to explain with the arrows and the underlined box. So in terms of leveling, it's also known as exploding or decomposing in the methodology of data flow diagrams. It involves using a series of increasingly detailed data flow diagrams to depict just one information system. It starts with an overview using a context diagram, seen over here, containing one single process as a symbol. And then for creating a diagram 0, it provides a more detailed view of the system as seen here. And system analysts continue to develop lower level data flow diagrams until all the processes are identified as functional primitives, so representing single processing functions. So, and I was just recently talking about keeping the integrity of the data flow diagram. And as you can see, we still have the entities around it. And the only thing that changes is what is being decomposed from this process into all of this. What is exactly happening in this process is all of this. And that's what's happening in this diagram 0. So more complex systems require more levels of data flow diagrams, with analysts working through numerous levels of identifying functional primitives. So for what exactly is balancing, right? So it basically ensures that input and output data flows are consistent between the parent and the child. So using the right terminology, more direct terminology, the parent and the child, it would be this one and then this one. So whatever is drawn from here, important entities have to be consistent here as well. So the process of balancing ensures that the data flows depicted in the parent data flow diagram are maintained in the child data flow diagram. So therefore, the system still works. It's just a more detailed view of it, more complex as well. Thank you very much for listening to this presentation. My name is Juan Pablo Izquierdo, and I hope everyone has a good rest of the day. This was for my information systems class at San Francisco State University.